website, digiprocenter.no. So yes, very well. Then I welcome you all, and I play the ball over to you, Aslak. So you can go ahead, please.
Thank you. So I'll try to share my screen. Maybe you have to shut down your presentation, Frode. I had to get some approval.
I will do that now.
There it is. Just a second. See my slides in full screen now?
Yes.
Okay. Yes, good morning, everyone, and thanks for the invite. I'm going to spend the next 30 minutes or so presenting an in-house software toolbox SINTEF has been developing named Bedrock. So the topic today is application of process data analytics and digital twin workflows. I also listed my good colleague Andrew Tobissen's name on the front page here. So since it's Andrew and I that have been the main contributors to the work I'm showing you today. So after a brief introduction, I'll open up the hood a bit and try to give you an overview on the core functionalities of this toolbox. And then wrap up with showing you some examples of applications where we have used this toolbox in projects at SINTEF. So I know you guys in the Cognitive congregation, you're focusing on digital twins. And for those of you who are here for some juicy digital twin stuff, please be patient. The slides should become increasingly interesting towards the end, but there are some basics we need to go through first. So first, a little bit about the Bedrock toolbox. So my group at SINTEF, we're working with chemical engineering in the Department of Process Technology. So the work with the Bedrock, it started out with the development of modular applications that were interacting with the OPC server in one of our pilot plants. So in order to establish accessible data pipelines that enables easy sharing of both real-time and historical data from the plant. And to connect digital twins to this was kind of where it started out. And back then, we see the logo here. And back then we saw this toolbox as kind of an underlying platform for establishing a range of other applications on top of. So hence the name Bedrock, which is kind of what we build mountains on top of. So that's quite ambitious, but that's at least the name of the initial code repository, and the name kind of stuck. So these days, Bedrock is a toolbox which we apply for flexible orchestration and deployment of various software stacks, meaning it can be used for essentially any application. So in the world of PowerPoints and digitalization buzzwords, framework names, they tend to sit a bit loosely. So in the following years, it turned out that almost any application developed in the group which involved use of this has kind of been given the name Bedrock. It's probably a good example of extremely successful branding or branding gone terribly wrong. So, but hopefully today we can do some clarifications regarding what it actually is. So in order to do that, we need to look a little bit under the hood. And I know we have a mixed audience here today. So someone will probably fall asleep due to my simplifications here, while other will pass out due to the complexity. So let's get started. So the motivation for the work started out with our experience around building modular applications consisting of various kind of software components. Examples of such components can be database servers, web applications, APIs, various clients and servers or brokers in relation to transport protocols. And also central to this is our in-house developed compute modules of various kind. And all these, they work together as an application in a stack. So such software applications deployed on bare metal has limited flexibility. So establishing a new application, for instance, on a new server, involves a lot of work can do. And so we quickly moved to Dockerizing the system. This does not get rid of the configuration. So even if how to say, despite nice multi-container tools like Docker Compose, we saw that configuring of the stack grew with increasing number of components, and this made like establishing of new deployments and changes to it. It had potential for a lot of work. So that's kind of the motivation for this work. We wanted to make a system where we could actually deploy such applications in a flexible way. And for us, the answer to that was the open source framework Ansible, which is kind of building a playbook with the hierarchical configurations, enabling a much easier way of deploying such stacks in a flexible way. So this is kind of the current menu these days on the toolbox we have. So how we define the courses in the menu here that it's increasing in size, and as soon as we have a component that is kind of configured to go into this hierarchical configuration stack, it becomes part of the menu. So the menu includes various type of database servers, communication modules, API frameworks, visualization modules, monitoring tools. So those are kind of the core components. But what's important for us is our in-house developed modules. That's kind of the important thing here. So and they apply these core modules as their infrastructure. So typically in-house modules, they are living in separate repositories, and they come into the framework as Git submodules, which also then are Dockerized and go into the stack in that way. So this slide tries to kind of illustrate how the toolbox is applied. We have a menu of different components, and we can then compose an application, picking selected modules from the menu, and then having a high-level configuration, enabling easy interplay between them. And we pull in sub-modules or in-house modules, and then we have an Ansible playbook, and we also have a list of available servers where they can be deployed. Yeah, I think this is the only slide with code I'm showing you today. This kind of shows the master playbook in Ansible, which is basically a menu where you pick the different modules. Of course, these can be configured on different levels in the repository here, but that's kind of where we save the time. So these are the menu of things we want to deploy in an application. On the left side, we see a selection of servers we have available. So we kind of then pick which machines should this application be running on. So in this case, we're deploying it on a set of servers. And then by pressing a couple of buttons, the repository can be from a central repository is then deployed to a remote server as an application, which is a Dockerized software stack that's hopefully running. And a server in this case, that's like a machine, could be deployed on your own machine, which we use often to kind of test and run things on our own machine. When we have it on a server that's available for others, that includes more users, and we have what we call a shared service, where we have more users to interact with this application. So this is very basic, but we can have them on-premise servers, which we use a lot, and you could also deploy it in the cloud. Doesn't really matter. And also what Ansible allows us for doing is to also deploy in parallel. We could deploy an application to 100 machines if we had that many servers, and we can also scale it depending on the loads needed. So that's kind of the basic to the architecture. So in order to wake up the digital twin guys, this application also involves interacting with physical plants and other data sources. So here we see a server, which for instance could be an OPC UA server from a POSIT plant. And the application is then communicating with this server in order to bring data into the workflow here. So we'll look more on that for the examples. And I actually come to the examples already. How much time I have spent? I'm a bit halfway about, so it's okay. So I'll show you 3 examples now on applications, how we've been using this. Not all are relevant for digital twins, but I'm showing it what it is now. The example in the end is probably the best example of a digital twin. So this first example is an example of how we use it in projects at SINTEF as a shared service for central databases with project web applications. And we use this, I've been using it with great success actually for collaborative work on process data analytics on a central data set. So this is a lot of boxes again, but the green boxes down here is kind of then the shared service, which is deployed with Bedrock. In this case, the application is a set of database servers, and it has a web app server, an API, has some clients for bringing data in. And in this case, we've structured this repository in a way that each project, this can serve many projects. Each project has their own database, which includes the data sets of the project in addition to a separate web application. And our developers then, in this case, they have a toolbox for data analytics they're working on, setting up a pipeline in order to bring data in. I mean, purpose of this is we've seen that we use a lot of time in order to structure data before we get to the machine learning and the interesting parts. So in this case, we have standardized database structures, and we have clients in the framework which can pull out data and bring the data through a pipeline of different operations. And this also enables, let's say we have a successful strategy for data analytics in one project, we can then just switch the data source and do exactly the same strategy on another data set quite easily. So this is part of how we can deploy applications or develop applications at SINTEF. So part of this, this is a whole toolbox on top of here, but it can be distilled into kind of pipelines that goes into an application. So this is kind of the structure, back to the other slides. So the application in this case, it's a database. It has web applications, API, and there's also a monitoring tool enabling the administrators to kind of monitor and get alerts and see how the stack is running. And there's a range of users then interacting with this. In this case, we've been using Timescale DB, which is a PostgreSQL extension. We like it very much because it enables fast, I mean, it's purpose-built for large time series of fast data. In addition, it still has the relational tables we have in Postgres. So this means we can connect the time series itself. I mean, the tags in these time series, they are related to sensors, where we can have tables on sensors information. And the sensors are linked to flow diagrams that can also be in the database here. We can have separate tables with calculated data, separate from the raw data. And in this case, we also even have separate tables for the web app itself, enabling us to kind of template out new web applications without doing any work. So this is just a slide showing an example of such a web app. All the information in this web application served from the central service is derived from information in the project found in the database. So it's all then populated with text and everything. And the project leader can then kind of manage the application for the users. So we see it as a tool where the user has access to visualization tools like dashboarding, inspecting databases, we can inspect and get quick access to flow diagrams in the process. In this case, we also see we have serving of documentation of in-house frameworks in order to aid the work. And we can have notebook servers in order to have interactive sharing of results and code. Yeah, this slide out. This is another example of how we can visualize other types of data sets. This is from a drone-related project, not so relevant. So that's the first example. On to the second example. Maybe it gets a bit more interesting for the digital twin guys now, because here we are interacting with a physical plant. So this example is an application we've been using a lot with success regarding one of our biggest pilot plants at SINTEF. So this is a shared service where we get access to real-time and historical data from the plant, and it enables interaction with digital twins and having a two-way communication with the control system of the plant. So then we're starting to talk about digital twins. So in this case, this is a structure. We can look to the left here first. This application is communicating with the OPC UA server of the plant. It has clients in order to do that. It has loggers, so it's logging data to a database. It has also visualization modules and APIs in order to access data. And in this case, we also have these cogwheels here, which are in-house modules. This is, for instance, a simulator we are developing, which is replicating the plant. So this is kind of a digital twin. It can go in parallel with the plant. And the modules here can also write set points back to the plant. So this enables testing of digital twins. So since it's a very nice sandbox, we have our own in-house process plant here with hundreds of tags. And we have good process simulators for it. So it's been a really useful exercise for us. So what we also see that has been a great success with this kind of setup is that earlier it was only the operator that kind of had access to the data in a good way. And when we run a project, it takes like towards the end of the project before the researchers get access to the data and start churning around on the data there. In this application has enabled the researchers to get real-time access to the data from their offices, meaning we could start working on the data immediately. We could put up stream processing here in order to produce values that typically are not produced until after the campaign is over. So we can get kind of real-time key performance indicators and other stuff. And we can also share data with customers. For instance, this is something we set up in the beginning of the COVID period, where we had customers from the UK that had to leave Trondheim. They were following the campaign with the operators. They had to go home, and then we deploy an application in the cloud, which is pushing the data sets to a database and has a visualization module, which enables the users to monitor the campaign real time. So that's been very useful for us. These are just examples of dashboards we can produce. It's also based partly on Grafana, which enables the users to actually build their own dashboard. So there's a lot of flexibility to this, which I see the researchers have been using a lot. So this also this kind of workflow also enables us to produce. We can kind of template reports and produce, for instance, a weekly report can be with access to the data in this way. We can very easily produce reports that took us a long time to establish. That can be done basically with the press of a key now. So it's time saving. So that's a little bit on towards digital twin. I think the last example here is the most relevant example for digital twin. In this case, we have an industry project with a Norwegian company where we're developing a digital twin for decision support and control of the process in a fish farm. So in this project, we've been working on developing a system that is well suited for early stage testing. We see that it often takes time before we are allowed to actually start tinkering with the process itself. And in this case, we are actually early stage setting up systems in industry without causing problem for the plant owners. And it also involves setting up data pipelines, which we'll see in the end. Yeah, This is a slide. The company we're working with here is called Nofutec. They're working on closed fish farms. See a picture of those here. And the core to our work here at SINTEF, of course, from the chemical engineering group, that we have established flow sheet simulator, kind of mimicking the process. So this is kind of the digital twin that goes into the framework. We're working together with a third-party company that is building the front end, which is typically dashboards like this for the operators. So that's a collaborating activity with a third party. In this case, architecture looks like this. I will come back more to the details in the next slide. But the point here is that we were encountering kind of a nightmare for the developers when the customer wants us to start testing on 3 plants at the same time. Of course, early stage prototyping of a system can be a nightmare if you have to do debugging in parallel on several plants. So in this case, the system suited this case very well, because we can deploy in parallel the same system to several plants. We're deploying them on edge machines in the plant. And when we do updates, we can push the updates to all the different instances. And it's also very easy to monitor kind of how things work centrally here. So it's been so far working out good. This is more into the details. In this case, the software stack deployed by Bedrock is the machines to the right here. Here we have the physical plant, which has its own control system with an OPC UA server and historian database and a human machine interface here. So in this case, we are using OPC UA as a transport protocol. The modules from SINTEF, we have the simulator here, and different plugins. They are all communicating with the OPC UA server, reading tags and running simulations, and then writing simulated tags and predictions back. So that means the simulator will produce new information, which can then again be applied by other modules in order to do different event-based operations. And then we also have built a REST API here in order to serve the web app of the third party, which is the pink box here. So this case, this means in order to have this system running, we need to establish new tags in the OPC server, because we're producing simulated data that needs separate tags. And that can sometimes, some process owners wouldn't like that, because it, of course, they have a process operating well, and they wouldn't like SINTEF guys to mess with it. So that's obvious. So in order to deal with that, we put up this system, which enables us to run operations with a read-only function from the OPC UA server. So that means this system can hook on. It's not interfering with the process at all. It only reads data. So it means we can come and install, and we could tear it down, and they wouldn't see any differences. So it's good for the process owners. In order to do that, we had to set up an internal OPC UA server, which is part of the Bedrock stack. It's replicating, or it's kind of mirroring the process server, and operating the same way with the interaction with the different modules. And here, of course, we have full freedom in how to establish new tags, and we have no black boxes there either, because all these OPC UA modules are in-house code from SINTEF. So we can kind of, it's code from us, enabling us to play around with this, which is good during prototyping phase. Of course, it's for an industrial application, you would like to have bulletproof solutions. But the good thing then is that we can just replace all these dark green modules with the industrial software very easily, since they're all based on standard protocols and databases. So in the final application, this can be robust software running here with then the core modules from SINTEF here in the same fashion. So what does it say? Yeah. So this kind of setup enables us to have early phase implementation of the digital twin, since it's not messing with the process, and it's not used for process control in this at this stage. It's decision support, and I think that's also how things start out. No one wants to connect let us set points here until it works. So starting out with decision support is a good thing. When we see that is going well, next step will be to start also controlling the process. So that's kind of next step of the process. So another important thing for this customer is that they want to have access to the data from the different plants, and we wanted to set up a pipeline bringing that data into some kind of central data analytics tools. So in that case, we also have set up Kafka, which is also part of the toolbox. So with Kafka, which is a great tool for streaming lots of data, this could also be used for the modules. I mean, in this case, the modules are communicating with OPC UA, but we could have flexibility. The communication protocol here could be MQTT or Kafka or other types. But in this case, we're also kind of in parallel bringing data into Kafka streams. And then we've been applying a KSQL DB, which is a very interesting tool, which is kind of a database built on top of Kafka. It enables a lot of interesting features for stream processing. It kind of covers a lot of workflow previously dealt with in Kafka with separate connectors and stream processing. So Kafka or SQL DB is a database that lets us do SQL queries on streams, and we can set up stream processing as part of those queries. And we can join different sources and have there's endless opportunities for what we can do then. We can have applications or modules communicating with the KSQL in relation to stream processing and event-based operations. We can also have, I mean, Kafka can have connectors. So we can also, for instance, listen to different databases and have all the information going into Kafka. Or other modules could kind of enrich the data flow. So there's many options here. And the endpoint here, the aim we're working on when we start having data here is that we can actually connect them, applications from different plants, bringing them into Kafka clusters, and then doing queries with joint tables. So we can have real-time stream processing of large data sets, bringing every second we can get updates on various things, and so it has a lot of potential. We haven't come this far, but this is kind of the end goal, and the infrastructure is there now. So we're starting to collect data, and this is where we're at currently. I think that was my last slide, and I think I spent about half an hour. So with that, I would thank you for your attention. I hope most of you are still awake.
Thank you, Aslak. Then we open up for questions, comments.
People are clapping even.
That's a good thing. I would like to ask you a question, Aslak, because when you work in product, you very often work together with clients, of course, and software suppliers and other R&D partners and so on. How do you exchange? Is that without trouble to exchanging data? I'm thinking about standardization. What is the status there?
I would say we try to stick to standard protocols that enables interoperability here. I mean, when you have OPC UA, which is a standard protocol, it's easy to communicate. And the same with MQTT or Kafka. And regarding security, I mean, that's a whole different topic. And for us here now, what the slides you saw here is kind of our prototype. Of course, when it comes to an industrial robust application, we would like to exchange some of these modules with industrial software. And since we operate with standard protocols, it's easy to do that. For instance, with the OPC UA, the clients and the server and the historian, everything can be replaced with the industrial software. Leaving it with the architecture is the same, but we have their modules there. And but the good thing is when we have no black boxes, we can do so much more during prototyping. For instance, we could play around with our own OPC server. We could put on, for instance, consumers or producers for Kafka as part of this very easily in the code, which is often the flexibility is less when we are having, if we would start out with an industrial software from day one. So that's kind of been the strategy. I don't know if it answered your question, Frode.
Yes, that was what I would like to hear. Yeah, thank you. I can also see that Johannes, you have raised your hand, Johannes, so please.
Yeah, I think this was very interesting, Aslak. And we have been discussing a little internally in Hydro two aspects. One is that when we do the first design of new processes, we do it together with SINTEF, we do it on desktop, we use 2 or 3 years calculating a lot of stuff, and then we go over to some laboratory experiment, maybe in our laboratory or in your end or a combination. And then there is not very much data, and these are very good system for handling that. But the next phase is more an industrial pilot where we create enormous of data very quickly. And then we see we need to store the data within our premises, which today is Azure or could be something else. And then we like the data to be in there.
Yeah, but that's obvious. And I mean, perhaps my slides didn't show that, but I mean, the data source does not need to be inside of our application in this case. I mean, we could query an external data source just in the same way as we interact with other external data sources. So that is probably the logical way to go in that case. So I think also we have a challenges, or we have plans at SINTEF in order to enable quicker implementation in industry on our things we're doing. I think often MATLAB scripts in SINTEF, they're miles away from seeing real life. So systems like this can enable kind of quicker implementation and bringing models to work with real data quicker. That's one.
I think that was Frode's question about standardization, and we discussed that in DigiPro together with Deloitte. We see in the oil industry, they are more occupied with standardizing more and more now to be more efficient and sharing method, structure, and things to connect easier. All the phases we're going through. This week, we in Hydro will host a meeting with NorSIC, the cybersecurity SFI in Norway, and they are interested in our experience from the cyber attacks we have and how we are now connecting the industrial system and protecting that. So I think this will be important issues in the year to come now. So work together with the cyber security guys, this flexibility, the methods, and see how we should work this in a more and more standardized way.
And in some ways, in some cases also it's logical to actually work within your own firewall, and this is kind of edge compute candidate as well. So it doesn't need to involve cloud. And I mean, often databases, they would like to stick. We would like to stick close to the data storage in order to also have the speed we need, and it does not necessarily include the cloud. So it's also on-premise compute this, but I mean, this system enables us to also deploy within the plant without exposing data.
Yep. Oh, very good. Thanks a lot for the information.
Yes, next one on the list is you, Marina, please.
It's on mute.
My headphone selected. Do you hear me now well?
Yep.
Thank you for the very good presentation. I am from SINTEF Digital Smart Data Group, and I have 3 short questions. You mentioned on one of your slides that you are using simulators for factories. What kind of simulators do you use? Do you program them yourself, or?
Yeah, I'm working in a chemical engineering group here, so that's kind of our core activity, is to build. We make models, and from those we make simulators. So we have a set of simulators. Some are, I would say, near commercial grade simulators with the graphical user interface and everything used in industry. Others are kind of mock-ups. So there's a range of different simulators we use. Typically based on flow sheet approach, but some can be very rigorous, taking into account physical and chemical things. Others could be, for instance, in the case of the fish farm, it's more like a pragmatic model, but there we have a flow sheet simulator system, which is in-house, that can enable us to also put in simplified models. and that can gradually be improved. So there's a range of different levels of the simulators there, but that's kind of the core. I mean, we're not an IT group here, so that's actually our core business, is to build simulators. That's why we have the pilot plant. We use the pilot plant to validate our simulators, and then in order to scale up processes, that's a very important tool. So there's different sets of simulators, but I think that's in the digital twin activities, that's kind of our main asset. It's our capability to actually build good process simulators. That's the core to it. So this Bedrock thing is just a wrapper to that, enabling us to do work on it.
I see. Then the second question, how many people worked on Bedrock?
Yeah, good question. It's not a long list. It's basically Andrew and I. We've had some prospects in, so it's probably a team of two main developers and a couple of more guys that has been doing kind of janitor work on our running systems. So we're kind of under critical there. So we have a strategy for in bringing more people in, but it's a small thing for now. So I mean, sometimes the name sticks and people think this is a large software organization or somewhat, but it's, I think, similar to many activities at SINTEF. It's like few people involved and a bit subcritical on that.
I see. And I have a third question. I saw that you mostly work with time series data, and you spawn many interesting databases and use standardized services as OPC UA. Do you also work with other data as images or videos?
We haven't been dealing with video in the Bedrock system, but basically there's option for it. We have some drone-related projects where we have a lot of sensor data and spatial data and geographic data, which includes, for instance, point clouds and images. Those we've been starting to put also into database structure, but not in the same extent as we do with time series. I mean 90% of what we do at Process Technology is related to time series of various kinds.
Mm-hmm. I see. Okay, thank you.
Next on the list, Steinar Kolos, please.
Yes, short detailed question. I noticed that you have labeled some of your data flow when it comes to OPC UA. You label it pub/sub. Is that related to the pub/sub in OPC UA, or is it only your way of say that you publish and subscribe to data?
Yeah, that's typically a client we build. It subscribes to a tag or a list of tags, and
Okay.
then server can or a client can also publish tags. These are event-based, so when there's a new data for a tag, it's published, and then the module subscribing to it will get that data and get started with event-based simulations or compute. So it's publish and subscribe function in the client.
So it's not related to the relatively new kind of protocol or technology in OPC UA. They call it pub/sub themselves there.
Yeah, I think we use the notation that we subscribe to tags in the OPC UA system as well. Yes, so it's a you can subscribe. You don't need to do a kind of a manual query in order to get data from an OPC server. You can also subscribe to tags and get them as the events happen.
Okay.
So I don't know how new that is, but yeah. So it's similar to what you have with other messaging protocols like MQTT and Kafka, as I see it.
Okay. Thank you, Steinar. Next on the list is Kjetil Tovanger, please.
Yes. So, just a small comment to this OPC UA and standardization. I just type in a comment here with this new user forum of OPC UA for the whole industry. That's starting up now, and the kickoff is 3rd of May, I think. So there will be more information on the side for the next coming weeks. So that might help. It's also both for standardization, user forum, and value out of OPC UA, and of course its connection to the OPC Foundation also. So that's just to recommend to involve there.
Thank you.
Yes. Yeah, you can write it in the chat as well, Kjetil. So
Yes, it is there.
okay, very good. Thank you. Yeah, no more hands. So yeah, okay. I also send in a chat the web address for digiprocenter.no where you can follow the planned events we have. Okay. And we will say thank you to you, Aslak, for a very interesting presentation. And what I hear from people and what I can see is that it's a lot of interest in Bedrock, and I know it will be more resources working with Bedrock as well in the years to come. Okay, thank you then.
Thank you.
And bye to all of you. Bye bye.
Thanks a lot. Bye bye.
Bye.
Bye bye.